So this is the last lesson for 5.3, which will be the last lesson before we take our test. So more than likely we'll review tomorrow, review Monday, test on Tuesday. So that way the boys have like one day to review with us as well.
Like the
So
quiz or the chapter test?
it's like a mid-chapter test because we're doing 5.1, 5.2, 5.3. So there's still 5.4, 5.5. Well, no, we're doing actually 5.1, 5.2, 5.3, and 5.5. So the only thing left is 5.4, but we're going to cover 5.4 and then probably do a chapter test with 5.4. Because 5.4 is intense.
Lovely.
Maybe. Maybe I'll just put it all in. Let me look at what I want to do at 5.4. To be determined. But that leads to today, which is the average value of a function. The average value of a function says exactly what you think it means. Average value. So the average value of a function is our integral from point A to point B of our function. But now, just like you do in the past, you're going to divide it by the average. So this example here says, suppose you wanted to find the average temperature during a 24-hour time period. How could you do it? Well, if f of t represents the temperature at time t, measured in hours since midnight, you would start measuring the hours at equal times. So maybe every hour on the hour, or every half hour. As long as it's at equal time measurements, it's fine. So you would look at all of those, and then to find the average, we would say, okay, we took the time for 24 hours. We started at midnight, or time 0. So that means we had 24 hours worth of time. Our integral would be the average, or the sum of all of those times from 0 to 24. And our function was f of t dt, because we were looking at the temperature with respect to temperature. So that's how you could go from the generic average value to finding it using an integral. And then you remember that this represents the sum of all the temperatures. Because an integral is really just a sum. So it's easy to see that the larger the number of measurements, the more accurately that we can reflect the average temperature. This can also be written as a Riemann sum by first noting that the interval between the measurements would be. So again, this is where you have to determine, okay, what are the increments between all of my measurements? If I make the increments 1 hour, then my time is delta t. If I make the increments larger, then my time could be delta 1, it could be delta 0.5, etc. Alright, so again, if we substitute that value, we're going to say that each of those increments are delta t now. So again, that represents our width. We substitute that value into our expression. So delta t in our Riemann sum is always kind of like at the end of that Riemann sum. And then it represents the summations of all of those times. So it would be like the sum of the temperature at time 1, the temperature at time 2, the temperature at time 3, so on and so forth. So as you work through that and you substitute all of that in, the last expression would give us the Riemann sum from 0 to 24 of my temperatures. And then if you wanted this to be even more and more, or you wanted it to be average, then same idea, you would multiply by 1 over 24. So do you think that there is at any point during the day that the temperature reading on the thermometer would be the exact value of the temperature? Does it logically make sense that at some point during the day, we would take a temperature reading and it would be equal to my average temperature? Probably more than likely, right? So if the average temperature for the day is 44 degrees, what that's saying is it likely at some point during the day the temperature was 44 degrees? Yes. So essentially, this is like the mean value theorem, but of integrals. So the average value is kind of like the slope of the secant. The temperature is like the slope of the tangent. So yes, I think it is very likely that at some point during the day, the average temperature is going to equal the actual temperature. Okay, next. If f is an integratable function on a to b, then we say its average value is, and again I kind of hinted at it, 1 over b minus a integral a to b of f of x dx. So it's the average of all the sums on the interval you are given, and then the sum of the area under the curve. So it's easy to think of the average value of a function as the integral over the whole interval, where b minus a is the length of the interval. So again, if you had 10 test scores and you wanted to find the average of your 10 test scores, back in the day you added up every score divided by 10. So that's all the average value does with an integral. So just having each of those scores, adding them up, dividing by the number of scores. So find the average value of f of x. Find the average value of f of x equals 4 minus x squared on the integral of 0 to 3. Does f actually take on this value at some point in the given interval? So again, you would need to do average value 1 over 3 minus 0, integral from 0 to 3 of 4 minus x squared dx. Find that value, so use your reverse power rule. 1 over 3 minus 0 is 1/3. Antiderivative of 4 is 4x. Antiderivative of x squared is 1/3 x cubed, and we are evaluating that from 3 to 0. One-third, 4 times 3 minus 1/3, 3 cubed minus 0. So 12. 3 cubed is 27. 27 divided by 3 is 9. 12 minus 9 is 3 times 1/3, and we get 1. So what that means is the average value of the function is 1. Set the original function equal to 1 to find the point at which the average value equals the original. So this represents my average value. And it says, does f actually take on this value? If so, where? So 1 equals 4 minus x squared. Subtract 4. Negative 3 equals negative x squared. 3 equals x squared. X equals plus or minus the square root of 3. But again, we know that the negative square root is not on the 0 to 3 interval. So it takes it on at root. So that leads into the mean value theorem, which is kind of what I've been like hinting at. The mean value theorem essentially says that the average value will equal the function at some value. So the average value is the integral part. The mean value aspect to it says that it will take on a point in that curve. So the mean value theorem for integrals basically says that if you are finding the area under a curve from A to B, then there is some number C whose function value will equal the value of the average value. So again, what represents the area under the curve? The integral from A to B. What is the area of a shaded rectangle? We talked a lot about that yesterday. It's the height times the base. The height is always the value on the function. The base is always the width of the rectangle. So essentially that f of c is my mean value theorem. So what we're saying is that the area of a shaded rectangle will equal the area under the curve. That's what the mean value theorem says. So we talked about the function will equal the average value, but that average value is coming from this shaded rectangle that we can create by taking the height at some point C, the width of the rectangle at A to B, and then manipulating that equation so it's f of c equals b minus a equal to the integral, which says the value of f of c is the average value because we divide by b minus a. Does that make sense, like where it came from and kind of like visually how it looks? Because for mean value theorem, it was always like, okay, here's the curve. Mean value theorem says that some horizontal line will cross that curve at least one point. So, what's the biggest rule for almost all functions? Continuity. So in order for an integral to be integratable, it must be continuous. So the mean value theorem and the average value theorem take on that same continuity property. So they say that if f is continuous on a closed interval from A to B, then there is a guarantee at some point C in that closed interval, the function at C will equal the average value of the integral. Okay, so another example. Find the average value of the function and the point at where it occurs. integral from 0 to 3 of x minus 1 squared dx. Average value says we have to divide that area under the curve by 1/3. Now, can we take an integral of something that is currently a function squared? No, we have to FOIL it. So we can't currently use our reverse power rule for this. I'm not sure numbers. Change it to a minus. Because if it's a plus, it can be a circle at once. Sorry. Yep. So, because it's a minus and not a plus, it ends up being the curve for a circle. So if we're going from -1 to +1, then we are going to find the area under the curve. That curve that we are looking at is a circle. That +1 shifts it up 1 unit. So origin is usually at 0, 0. The +1 is going to shift it up 1 unit. The negative out in front is going to reflect it. So my circle that normally looks like this is going to get reflected, so it's going to look like that. So it's going to be a reflected circle whose area is going to be under the circle and bounded by the x-axis. So we are looking for the green space. If you did not know how to do your reverse power rule, because then it is that circle and that geometric characteristic, and just to kind of review our geometry, what you could do is make this an entire rectangle. So the height of the rectangle would be this point right here, or the point over there. So it's like saying, oh, what is f of 1 or f of -1, which are both equal to 1 minus 1 squared. So 1 minus 1 squared ends up becoming 0, square root of 0, 0 equals 1. So both of my endpoints are at a height of 1. So that means the area of our rectangle, so that f of c, and again, intentional, b minus a, right? F of c, b minus a, so I get that the area of the rectangle is 2. And then the area of the semicircle is going to be 1/2 pi. Radius is 1. So we have 2 minus 1/2 pi, which would represent the green shaded space. So the purple is 2, the green is 1 minus 1/2 pi. So that area represents the area under that curve, half is 1 over b minus a times all of that. So the average value of f is 1 minus 1/4 pi. And again, if you think about like the 1/4 pi, 1/4 pi is 1/4 of 3. So half of 3.14 is 1.57. So it's even half of 1.57. So you're looking at like 0.75-ish. So that means that we would need the function f of t to equal that 0.75-ish. Yeah, I feel like I meant to delete this one because that example 3 is my example. I gotta go look at this. I'm also like copy and pasting and move things and never fix, like never re-delete it. Cause like I feel like this example is harder than like the one I wanted to do. So it's like not harder, it's just different. So again, this represents my average value. So up above where it says when does g of x take this value on, that is my mean value here in past. So we want to know when does this equal that. So is it the bottom the negative? Yeah. Yeah, I think I meant to delete my top one. Because that would make way more sense because then you have my next example I skipped. So we'll go backwards to it. Okay. Average value, and then it would be a calculator question to honestly find where they equal. So you would set 1 minus b squared to the 1/2 equal to 1 minus 1/4 pi, where this goes in y1 and this goes in y2, and then you solve for t. So we can do that. You can also check, because it's an average value on a calculator, your equation to make sure you've got the correct area under the curve. I would change my window to be -2 to 2 so that I wasn't looking like anywhere crazy. And again, if I can predict my average value is somewhere in that point, like 5 to 0.75, you can make your y values like 0. So I see that original curve that we drew up on the board and is in green. And then I can see that the average value crosses that blue curve twice on my interval. I would find those points by doing second trace intersect. And I get that it occurs at t equals 0.618. And then it would also occur at t equals -0.618. Because it's symmetric. So we got So going back and looking at other examples, we're going to look at this in two ways. We can find this integral's average value by hand, and then we can use our calculators and use the NINT to determine if what we found by hand is correct. So if you have the integral of x minus 1 squared, we don't have a quote-unquote chain rule yet for integrals. We will eventually get one, but for now it's like the product rule. We have to simplify x minus 1 squared and turn it into a FOIL function. So I'm going to manipulate x minus 1 squared and say that's x minus 1 1, which I'm going to say is x squared minus 2x plus 1. Because now I can take the integration of x squared minus 2x plus 1 on my interval from 0 to 3 and find its average value. One of the things that's important, and I can't stress it, I always show it, making sure you always have your dx, making sure you always have your bounds, and then once you find your integral, just keeping it consistent. So I'm going to bracket my antiderivative because I've got 1/3 out in front. So I get 1/3 x cubed minus 2x squared over 2. So those 2's cancel, plus x, and again, integrating from 3 to 0. That 1/3 is sort of just tagging along right now. We're going to ignore it as I plug in my values. So 3 cubed is 27 over 3, minus 3 squared, which is 9, plus 3, minus what I love is 0, 0. So then 27 divided by 3 is 9. 9 minus 9 is 0. 3 divided by 3 is 1. So I see that once again my average value is 1. We can confirm that average value by going on our graphing calculators. You'd hit alpha y equals, so you can get your fraction. You would put the 1/3 in front of your integral. So you're finding that average value, you can put the 1/3 out in front. Then hit math 9, goes 0 to 3. You can type in the original, so you can type in x minus 1 squared. You don't need to type in your FOIL form. And then confirm, we get 1. So it says at what point in the interval does the function assume its average value? So now you're going back to algebra 2 again, and you are saying, okay, when does x minus 1 squared equal 1? So this is a solving by taking the square root. So you would take the square root of both sides. That would allow you to get rid of the squared over here. So you have x minus 1 equals, here's the trick, it equals plus or minus the square root of 1, or plus or minus 1 in this case. Because when you take the square root, you bring the plus or minus. If the square root's already there, it stays just a normal square root. But when you take the square root, you know the plus or minus, because remember, anything squared can be positive or negative. So then we say x minus 1 equals 1, or x minus 1 equals negative 1, which means x equals 0. Try to write it over there. And then if you add 1, x equals 2. So both of those are actually in my interval. So both of them are solutions, which means the average value occurs twice. So it only guarantees that it occurs, it doesn't guarantee how many times. So it can occur 2 times, 3 times, 5 times, or 1 time. It just guarantees it happens. So let's make that one final connection. F of x as a capital F is an antiderivative. It is the antiderivative of lowercase f of x. Capital F prime of x is the same as lowercase f of x. And then capital F of x equals x squared is what we call the antiderivative of 2x. So antiderivative and integral mean the same. Antiderivative and integral mean the same. So anytime I ask you to find the antiderivative, it is the same as me asking you to find the integral. And then the last part is just kind of like a review of problems we did the other day. So do you know how to take the antiderivative of the integral from 0 to pi halves of cosine x dx? Do you know how to take the antiderivative of -1 to 2 of 3x squared? And then the bottom one, you have an x squared in a square root. So what does that look like? Or what would that represent? So it's not a natural log, because you don't have the derivative of x squared up above. So right, you remember when we have like the square root of 1 minus x squared? It is an inverse straight. You nailed it. So if it's, we did tangent the other day, tangent has no square roots. So that means it's the inverse sine. Alright. Antiderivative of cosine x is, yes, but it needs no negative this time because it starts with an x. So antiderivative of cosine is positive sine. We're evaluating from pi halves to 0. So pi halves of sine, 0. Sine, or 1. Sine 0 is 0. 1 minus 0 is 1. That 3 out in front is super nice in my next problem because add 1, you get x cubed. Divide by 3. Divide 3s. So antiderivative of 3x squared is x cubed. Plug in your 2 and -1. Be really careful though, because that -1 cubed stays negative. And then you have that negative in front, so it becomes positive. So we end up with 8 plus 1, or 9. And then the bottom one is inverse sine, which is why its bounds don't have trig functions in them, because you are looking for the trig functions at which they occur, or the radians, I guess, at which they occur. So we're bounded from 0 to 1/2. So when does the sine equal 1/2? What? And then when does the sine equal 0? 0. So, wait, what am I doing in my head? I think it is left side. The sine climbs. Sorry. So sometimes it's a good trick. Alright, 305, 11 to 35. So 11, it's at odds. And then 40, and then 45 to 50. The 11 for the 13 are the use the NIMT, then like 15, 16, 17 are average values with area under the curve, like we did with the circle. And then there's actually some that are just like definite integrals. So the only thing you have to know, kind of, and put it in your notes, the integral of e to the x is e to the x. So it's in your notes, but I know it popped up on one worksheet and it pops up on your notes. So that's the only thing you need to know. And then that's pretty much find average values.